Hello students, this clip will let you know how to design an helical spring. Considering a small example as shown here, design a helical compression spring to carry a load of 500 Newton and a deflection of 20 mm. The allowable shear stress in the spring material is 350 meganewton per meter square and the modulus of rigidity is 82.7 into 10 raised 3 meganewton per meter square. The spring index is 6. And the data handbook used in order to solve this example is of K. Balve Reddy and K. Madhavan, 3rd edition. Sorting out the given, as the first given would be a load of 500 Newton, further moved ahead with a deflection of 20 mm, and allowable shear stress 350 meganewton per meter square. I converted that into Newton per mm square, which states to be 350, and the modulus of rigidity 82.7 into 10 raised 3 meganewton per meter square. It is be equal to 82.7 to 10 raised 3 Newton per mm square, and spring index is 6. And to determine or to derive would be D, as you can see in the sketch, the D would be a diameter of a wire that is being used to develop a spring, and capital D would be the mean diameter of a spring. DO will be outer diameter and DI will be inner diameter as seen over here. I is a number of turns, I dash is a number of active and inactive turns, LS would be solid length as shown here, and LF would be a free length, and P would be a pitch, the distance between two consecutive springs. Solution. Now step 1 is to find the diameter of a wire small d. From the data handbook, setting a shear factor which would be K is equal to 4C minus 1 divided by 4C minus 4 plus 0.615 divided by C, the equation 11.2b of page number 139 of a data handbook. Now substituting all the values as in given, the K would be 1.2525. We know that C would be capital D divided by small d, which is a spring constant. And now therefore equating that, the capital D would be 6 into small d. I took it as an equation 1. From the data handbook, considering a shear stress formula, tau is equal to 8 F dk divided by pi dq, equation 11.1a of page number 139. Substituting all the values in the above equation, and D is equal to 6D as per the equation 1. Therefore, substituting all the values, it comes somewhere like this. By this, the D would be derived. Therefore, the small d would be 5.23 mm, which is a diameter of a wire. Further, the step 2, the mean diameter of a spring, capital D, need to be derived. From the equation 1, we know that in earlier slide, capital D would be 6 into small d. And small d, what we derived in our earlier slide, would be 5.23. Then 6 into 5.23, then the capital D would be 31.8 mm, which is a mean diameter of a spring. Then step 3, to find outer diameter of a spring, which would be DO. The equation is DO is equal to small d plus of capital D. Therefore, substituting both the values, the outer diameter would be 31.7 mm. In a similar way, the step 4 is to find the inside diameter of a spring, DI. The formula states to be DI is equal to capital D minus of small d, difference of those two diameters. Therefore, substituting the values, then DI would be 26.57 mm. Step 5, moving ahead, would be to find the number of turns in a spring. From the data handbook, the deflection formula states to be 8 FDQ I divided by GD4, equation 11.5a, page number 139 of a data handbook. Therefore, equating this and coming out with an I would be Y GD4 divided by 8 FDQ. Substituting the values in the above equation, I would be 9.6. I hold it down into 10 turns. Now step 6 is to find the solid length, free length and a pitch of a spring, LS, LF and P. Assuming the spring ends are of square and ground end, and from a table 11.7 of page 152 of a data handbook, the total length I dash would be I plus T, I plus 2, where turning it would be 12 turns. Then solid length LS, I dash into D, I dash is derived in an earlier one. Substituting the values, we get 62.76 mm. Therefore, the solid length of a spring that's shown over here would be of 62.76 mm for this case. Therefore, the free length LF would be LS plus Y plus I dash minus 1 into 1 mm. Substituting all the values over here, the free length that we get is 93.76 mm. That free length replicates somewhere over here as shown in this figure. Further, we know that LF is equal to IP plus 2D. Therefore, substituting all the values in the formula, the pitch P would be 8.33 mm. That's shown over here in this figure. Thank you.